A wall of concrete stretching across one of Asia's greatest rivers once altered the timing of the planet itself, if only by a fraction so tiny that no human being could ever feel it. Yet the measurement was real. The numbers were calculated. The mass was so enormous that scientists determined Earth's rotation slowed by a microscopic amount after the reservoir filled behind China's Three Gorges Dam. A single day became longer by roughly 0.06 microseconds. The planet's shape shifted ever so slightly. The axis moved by nearly 0.8 inches, or about 2 centimeters. Now China is preparing something even larger. How large must a structure become before it starts interacting with planetary physics instead of merely reshaping landscapes? At what point does a dam stop being a regional infrastructure project and become a force capable of redistributing mass on a continental scale? And if one reservoir could measurably influence Earth's rotational behavior, what happens when an even bigger hydropower system rises in one of the world's most geologically extreme regions? Those questions are no longer theoretical curiosities buried in scientific journals. They are becoming part of a rapidly intensifying global discussion surrounding China's next generation of megadams. Projects designed not merely to generate electricity, but to redefine energy production, water control, industrial security, and geopolitical influence across Asia. For years, the Three Gorges Dam stood as the symbol of modern China's engineering ambitions. Built across the Yangtze River in Hubei province, the structure expanded into the largest hydroelectric power station ever constructed. The dam stretches roughly 7,660 feet, or about 2,335 meters, across the river and rises approximately 607 feet, or 185 meters, above the riverbed. Behind it sits an immense artificial reservoir extending hundreds of miles inland. The reservoir stores around 40 cubic kilometers of water, equal to nearly 10 trillion gallons. That water mass rests approximately 574 feet, or 175 meters, above sea level. According to calculations widely circulated through scientific and media discussions over the years, concentrating such an immense amount of water at elevated altitude redistributed enough mass to slightly increase Earth's moment of inertia, slowing the planet's rotation by a microscopic fraction. The effect was extraordinarily small. No clocks required adjustment. No sunrise changed enough for anyone to notice. Yet the symbolism was powerful. Humanity had entered an age in which infrastructure could theoretically interact with planetary-scale physical systems. China's leadership understood something else as well. Massive hydropower projects were not only about electricity. They represented industrial dominance, long-term water security, regional flood management, transportation control, and strategic economic planning measured not in election cycles but in generations. The Three Gorges project emerged from decades of political debate and technical planning before construction officially accelerated during the 1990s. When the reservoir finally filled in stages during the following years, entire cities disappeared beneath rising water. More than 1 million people were relocated. Ancient settlements vanished. Hillsides became unstable in some regions surrounding the reservoir. Concerns over landslides, sediment buildup, and ecological disruption followed the project almost from the beginning. Yet the scale of the energy output transformed China's electrical landscape. The dam's installed generating capacity exceeded 22,000 megawatts, enough to power enormous urban and industrial regions. It became a central pillar in Beijing's long-term attempt to reduce dependence on coal while supporting the country's manufacturing expansion. During periods of peak operation, the station generated more electricity than entire nations consume annually. But even before the global fascination surrounding the Earth rotation calculations emerged online, Chinese engineers had already begun thinking beyond Three Gorges. The country's hydropower expansion did not stop with a single mega-project. Dam construction accelerated along the Jinsha River, the upper section of the Yangtze. Massive facilities such as Shiluodu, Wudongde, and Baihetan followed. Baihetan alone became the world's second-largest hydroelectric station, capable of generating around 16,000 megawatts of electricity. Its reservoir stores more than 20 billion cubic meters of water. The progression revealed a clear pattern. Each project expanded engineering capability, logistical coordination, turbine efficiency, transmission capacity, and high-altitude construction expertise. China was effectively building a ladder toward increasingly extreme hydropower ambitions. Then attention shifted westward toward Tibet and the deep river gorges descending from the Himalayan plateau. Few regions on Earth contain more untapped hydropower potential. Rivers born from glacial systems in the Tibetan plateau plunge through narrow mountain corridors with extraordinary force. Elevation drops measured over relatively short distances create immense kinetic energy potential. For hydropower planners, these rivers represent some of the most powerful renewable energy resources on the planet. Among them, one river stands above the rest in strategic significance: the Yarlung Tsangpo. Flowing across Tibet before curving dramatically around the eastern Himalayas, the river eventually enters India, where it becomes the Brahmaputra. Along one section near the massive bend around Namcha Barwa Mountain, the river descends through one of the deepest canyons on Earth. The vertical drop in elevation across this region creates hydropower potential far beyond what Three Gorges could achieve. Chinese planners have studied the region for years. Reports emerging through state-linked media and international coverage indicate that Beijing is moving toward construction of an enormous hydropower complex, potentially valued near $165 billion. Some projections suggest the facility could generate more electricity than the Three Gorges Dam by a substantial margin. The implications extend far beyond engineering statistics. Unlike the comparatively accessible Yangtze Basin, the Tibetan Plateau presents one of the harshest construction environments on Earth. Thin air, seismic instability, extreme terrain, landslide risks, freezing conditions, and logistical isolation complicate every phase of development. Roads, tunnels, worker housing, transmission systems, and supply chains must all be established across mountainous territory where geography itself resists large-scale construction. China nevertheless possesses advantages no other country currently matches in this sector. Over the past 2 decades, the country has built the world's largest high-speed rail network, some of the planet's longest bridges, vast coastal ports, entire industrial cities, and enormous renewable energy systems. Chinese state-owned engineering firms accumulated unparalleled experience in concrete megastructures, long-distance power transmission, mountain tunneling, and mass relocation logistics. That industrial capability is now converging on Western China. The proposed Tibetan hydropower developments arrived during a period of mounting energy pressure inside China. Electricity demand continues rising despite slowing economic growth compared with earlier decades. Expanding electric vehicle production, artificial intelligence infrastructure, semiconductor manufacturing, and urban electrification require immense amounts of reliable power. Coal still dominates much of China's energy system, but Beijing faces increasing pressure to reduce emissions while preserving industrial output. Hydropower offers a strategic solution because, unlike solar and wind energy, dams provide stable baseload generation and large-scale storage potential. The geographic imbalance within China's economy also shapes the project's importance. Much of the country's industrial and population concentration lies in eastern coastal provinces, thousands of miles from western river systems. To solve this imbalance, China spent years constructing ultra-high-voltage transmission corridors capable of transporting enormous quantities of electricity across vast distances with reduced losses. The concept is simple but massive in execution. Energy generated in remote western regions can feed eastern manufacturing centers and megacities. Hydropower from Tibet could eventually flow into economic corridors supporting hundreds of millions of people. Yet every expansion into mega dam construction carries escalating environmental complexity. Reservoirs fundamentally alter river systems, sediment transport changes, fish migration patterns collapse. Local ecosystems transform. Flood cycles shift. Groundwater systems respond unpredictably. Entire valleys disappear beneath artificial lakes. The Three Gorges experience demonstrated both the power and the cost of such transformation. Satellite observations and environmental monitoring around the Yangtze Basin revealed changes in regional precipitation behavior and land surface temperatures after the reservoir reached major filling stages. Meanwhile, geologists and hydrologists continued examining the relationship between massive reservoirs and seismic activity. Large reservoirs do not directly cause major tectonic earthquakes in the conventional sense, but the immense weight of stored water and the infiltration of water into subsurface rock layers can influence stress conditions along existing faults. This phenomenon, known as reservoir-induced seismicity, has been observed near some dam systems around the world. That concern becomes more significant in Tibet because the Himalayan region already ranks among Earth's most tectonically active zones. The Indian plate continues colliding with the Eurasian plate, slowly forcing the Himalayas upward. The same geological processes that created the world's tallest mountains also produce powerful earthquakes. Building gigantic reservoirs within such terrain introduces layers of engineering risk unmatched by most earlier hydropower projects. China's planners appear fully aware of these dangers. Modern dam construction in the country increasingly incorporates advanced seismic monitoring systems, slope stabilization networks, satellite deformation analysis, and high-capacity spillway engineering. But the scale of the proposed Tibetan systems pushes existing experience into new territory. There is also another dimension shaping international concern: water geopolitics. The rivers descending from the Tibetan Plateau do not belong solely to China. They flow into multiple Asian nations, supporting hundreds of millions of people downstream. The Brahmaputra system, in particular, carries enormous importance for India and Bangladesh. Any large upstream water project inevitably raises fears over future water control, seasonal flow alteration, or geopolitical leverage. Chinese officials have repeatedly emphasized that proposed hydropower systems are primarily run-of-the-river projects designed to generate electricity rather than permanently divert massive water volumes. Nevertheless, downstream governments remain cautious. Water security increasingly defines strategic planning across Asia. Climate change is altering glacial melt patterns, monsoon behavior, and seasonal river flow variability. In such an environment, control over upper river systems becomes politically sensitive. Meanwhile, inside China, mega dams are increasingly viewed as symbols of technological state capacity. The Three Gorges Dam once represented a singular achievement. Today, it resembles the opening phase of a much broader transformation. Chinese hydropower engineering expanded from large dams into integrated systems involving interconnected reservoirs, long-distance electricity transmission, smart grid coordination, and increasingly automated infrastructure management. The scale of investment reflects that ambition. Hydropower projects require enormous upfront capital, but can operate for decades once completed. They create employment during construction, stabilize electrical supply, reduce imported fuel dependency, and support regional industrial development. For Beijing, such projects align with long-term state planning objectives, extending well beyond immediate financial returns. At the same time, climate pressures are intensifying interest in large renewable energy systems globally. Extreme heat events have increased electricity demand for cooling across Asia. Severe droughts periodically reduce river levels and strain hydropower generation in some regions, while catastrophic flooding elsewhere underscores the continuing appeal of flood control infrastructure. Governments worldwide are attempting to balance decarbonization goals against energy security concerns. China's approach differs from many Western renewable strategies because it relies heavily on centralized mega infrastructure. Instead of dispersing generation entirely across smaller local systems, Beijing continues favoring enormous state-directed projects capable of reshaping national energy flows. That philosophy explains why discussions surrounding the new Tibetan hydropower systems increasingly sound less like conventional infrastructure planning and more like continental engineering. Some of the proposed facilities may involve cascading dam systems rather than a single isolated structure. Water descending through successive elevation drops could generate electricity repeatedly across multiple stations. Tunnel systems bored through mountains may redirect river flows toward optimized turbine corridors. Entire valleys could transform into coordinated energy networks. Engineering on this scale requires unprecedented quantities of concrete, steel, heavy machinery, explosives, and transmission equipment. It also requires political authority capable of mobilizing enormous labor forces and financing structures over many years. China possesses both. The deeper China advances into the Himalayas, the more the project begins resembling something beyond a conventional dam. Plans associated with the Yarlung Tsangpo hydropower complex increasingly point toward a network of tunnels, cascading stations, diversion systems, underground turbine halls, and interconnected infrastructure spread across one of the most dramatic river corridors on Earth. Some estimates place the future generating capacity near 70 gigawatts, roughly 3 times greater than the Three Gorges Dam. Annual electricity production could approach 300 billion kilowatt-hours, enough to rival the yearly electricity consumption of major industrial nations. The geography explains why Chinese planners have pursued the region for decades. Near the Great Bend of the Yarlung Tsangpo River, water plunges through a dramatic elevation drop of nearly 6,560 feet, or about 2,000 meters, across a relatively short distance. Few places on Earth combine such steep descent with such enormous water volume. Hydropower engineers see concentrated gravitational energy on a scale almost unmatched anywhere else. Unlike the broad reservoir system behind Three Gorges, the Tibetan project may rely heavily on a run-of-the-river approach. In simplified terms, engineers divert portions of river flow through tunnels or channels, force the water through turbines, then release it downstream again. This design can reduce the need for one gigantic standing reservoir, although substantial water regulation systems still remain essential. That distinction matters because much of the public fascination surrounding the Three Gorges Dam, slowing Earth's rotation, came from the immense quantity of water stored at elevated altitude. The redistribution of trillions of gallons slightly altered Earth's mass balance. By comparison, the Yarlung Tsangpo system may generate far more electricity while storing comparatively less water in a single giant basin. Some engineers and researchers therefore argue the newer project may not create the same type of rotational effect despite its much larger energy output. Still, the numbers surrounding the new project remain staggering. The Yarlung Tsangpo project may ultimately become less remembered for the question of Earth's rotation and more for what it represents geopolitically and technologically. It stands at the intersection of renewable energy transition, climate pressure, water security, territorial strategy, industrial competition, and engineering ambition. Its success or failure could shape regional politics across Asia for decades. If completed according to current projections, the hydropower complex would likely become the most powerful hydroelectric system ever constructed. It could reinforce China's energy security while accelerating electrification across major sectors of the economy. It could also deepen international anxiety over transboundary rivers and upstream infrastructure control. Meanwhile, the environmental consequences may unfold slowly over generations rather than immediately. River systems evolve over time. Sediment transport changes gradually. Ecological impacts accumulate season by season. Mountain infrastructure reshapes transportation and settlement patterns. Reservoirs alter landscapes permanently. The Three Gorges Dam already transformed central China physically, economically, and environmentally. Entire valleys vanished beneath water. Shipping patterns changed. Flood management systems evolved. Regional energy distribution shifted dramatically. The Tibetan projects could eventually trigger changes on even larger geographic scales. That possibility explains why the world continues watching so closely. A single dam once slowed Earth's rotation by an almost immeasurable amount and became a global symbol of engineering scale. Now China is moving toward infrastructure potentially several times larger, deeper inside one of Earth's most extreme landscapes, connected to rivers that cross international borders and support hundreds of millions of people. The project reflects a wider reality defining the 21st century. Human civilization is no longer merely adapting to the planet's geography. Increasingly, it is redesigning that geography itself.